I'm really excited that I have a problem to post today. This is partition string into substrings with values at most k. Okay. So you're given a string S consisting of digits from 1 to 9 and an integer k. So you're given a number, essentially, right? But the number doesn't have any zeros in it. A partition of a string S is called good if each digit of S is a part of exactly one substring. Okay, so you have to partition the string. You have to make a decision about where you're going to split the number up. And the value of each substring is less than or equal to k. All right, so we have this k constraint, so we're going to split up this substring into a series of numbers, right? Each of those numbers in that series have to be less than or equal to the given value k. Return the minimum number of substrings in a good partition of S. So you're trying to minimize the number of splits that you're going to do to get this case where all the numbers you split are less than or equal to k. If it's not possible, so if no good partition of S exists, return -1. How would that happen? Well, if k is greater than 9, right, you can always partition because, you could, if k was 10, right, I guess the idea is if k was 10, so before I continue, just to think about what would mean if you didn't have a good partition, regardless of what this number is, right, even if this was all 9s, you could partition here and here and here and here and here and here because x can only be 1 to 9, right? So if k is 10 or greater, you can always partition the string, right? For example, if these were all 9s, well, how would you partition the string? Well, you could do one partition here and one partition here and one partition here, 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 here. So the only time you return -1 is if k is less than 10, right? If k was 5, well, I can't make a partition that's less than 5, right? Because there's a 9 here. I'm stuck in this slot with a 9. I can't split up this 9 anymore, right? I can only split up this system up until they're being at least, right? The least amount I can have in the system for each split is 1 digit, right? So if I can only have 1 digit in the spot and k equals 5, well, then there's nothing I can do. I can't keep splitting on this, right? The difference was when k was equal to 10, right? When k was equal to 10, I started with this whole system of 999, whatever, but I can split it up into 9999 and be like, okay, actually that's still bigger than 10. I can split it up to 99. Okay, that's still bigger than 10. I can split it up to 9. All right, just the 9 alone is less than 10, so I have a split that exists. Of course, it's kind of a bad split. If we want to minimize the number of splits, we don't want to keep having to split every single number, but at least the split exists. But if k is less than 10, there could be a case where you can't split because you split up to 9 and you can't split anymore, and it's still greater than the k value you're trying to use. Okay, so that's where -1 exists, and we'll just have to incorporate that fact into the problem somehow. Okay, so note that, so we're here, note that the value of the string is the result when the interpret as an integer. For example, yeah, like we were saying earlier, right, you're just given a string 1, 2, 3. If you were to split it at 1, it would be 1 and 23, right? A substring is a continuous sequence of characters. Yeah, we know what a substring is, at least I hope we do if we're approaching this medium problem. So S equals 165462, K equals 60, output equals 4. So how does that happen? Well, if you have the string given as 165462, this is S, and then K equals 60. Sorry. Well, if we did this split here and another split here, and unfortunately we could do a split here and another split here, right? And then we get 4 splits. right? So there's 4 strings that are created, so we output 4. Note that we could also split like this, and it would give you an identical length, right? So there's not necessarily one unique split in the system, but it does seem kind of like a difficult problem, right? Because like depending on where you split, you could get a different result, right? Depending on where you split in the system, you know, now like if you split here just the 5, then you have the 5, but if you use the 4 as well, right? Now the 4 is used with the 5, and then you have to consider the 6 alone. So it's a little finicky, right? It's a little strange. So how do we approach this problem? Before we do that, let's just, you know, look at both examples. Sorry. When k equals 5, right, we have that example where k is less than 10. You'll notice since one of the digits is greater than 5, no matter what you do, if you have an 8 in your system, it's going to be greater than 5, so you have to return -1, so there's no good substrings. Okay, so for this problem, intuitively, right, first thing you notice, even if you don't get the proof, just from how the problem is solved itself, right, when you have k equals 6, you'll notice that there's something there's a pattern here. So sometimes you can use the example problem and the example solution, the explanation, as kind of a hint in itself to how this problem should be solved, because sometimes it'll reveal the nature of the solution. You'll notice that, you know, we had multiple solutions that I showed, but it chose this one. Right? It chose this solution in particular. So the fact that it chose this solution in particular versus the other solution is what revealed to me, or at least implied some information about the nature of the solution itself. Because what you notice is like, what we kind of do to get this solution, right, is we look at one and we say, is one itself the solution? And we realize, well, we can do more than one because oh no, that happened. I apologize today. If x is 60, right? If we use just one, we're not using our full potential, right? Because we can fit at least 60 in each partition. So we start with one whole partition, which is the whole string. We look at just one and we say, well, yeah, sure, we could split on one, but we're not really using our full potential here, right? Because 1 is less than 60, so I could probably use the next number as well. Then I look at the next number, and now I have 16. I'd say, well, yeah, 16, I could still fit that in one partition, but maybe I can fit something else as well. So then I look at the next number and I say, shoot, 165 is too big. I can't fit this in. So whatever I previously thought the solution was is the actual solution, right? And now that I've split that in one partition, I restart my count and I say, okay, 5. Can I fit 5 in here? Yeah, 5 is less than 60, so I can definitely use that. Well, let's check the next thing. 4. Yeah, 4 is less than 60, so I can definitely use that. Right, so I have 54 less than 60. We're good. Let's try the next thing. Oh, shoot, I just overshot. Now I'm at 546. It's too big. So I'll just use those two and restart the count. I choose 6 and I say, yep, 6 is less than 60. So maybe I can get something better if I try my luck. I try my luck and I get 62 and I say, oh, shoot, 62 is greater than 60. I can't use that. So now I partition again. And then I do the same thing with 2. And you'll notice that this is the solution that is used in the explanation. So the idea is very greedy, right? The idea is just keep trying to add to your partition until you can't add to it anymore, right? And when you can't add to it anymore, then just know, okay, I guess I went too far. Whatever the previous sum is that I found, that'll be my previous split. and I'll just continue from there, right? I'll just greedily add to my select like current partition until I can't anymore, and then I'll split. And that is the solution. And intuitively, that kind of makes sense, right? I'm not going to give a formal proof. You could probably find a formal proof in the discussion. But if you think about, like, if I want to use 1, I'm going to have to use 1 and 6. I'm going to have to use all the numbers in a partition, right? So I might as well use 6. Because if I don't use 6, then 6 is going to have to be used in another partition. So it's only going to increase the number of partitions that I'm going to create, right? And that's where it's very greedy, right? There's probably a greedy proof, probably a proof by contradiction, which can be kind of confusing. But the idea is, like, intuitively, right? If I want to use, I'm going to have to split on this value regardless. So if I don't split on it now when I can, I'm going to have to do it in the future. So if I have to do it in the future, I'm going to have to split on it in the future, so it can only be worse. It might be just as good to do it in the future, but I'm still going to have to split on in the future, so I might as well just do it now if I can. Right? If I don't split, right? If I decided I could fit the 6 in my partition and make it 16, but maybe it's better not to, well, I'm going to have to split on that 6 later anyways. So that's only going to increase the size of my next partition. Right? Since I'm not using it now, I'm going to have to use it in the future. So now on my next split, I'm going to have to use it. And oh, look at that. I can't fit it. Right? So if I don't use something that I could use now, I'm basically just procrastinating using it in the future. So using in the future can't give me a better score. It can only be just as good. That's a hand-wavy way of saying that the solution is just try to fill up what you currently can and fill up until you can't, and move on and try to fill up again. Right? A very greedy approach. Now, that intuition was gained from the explanation, right? Because we noticed that there were multiple solutions to this problem that gave us a partition size of 4. Yet, they chose a very specific one. So the fact that they chose a very specific one is not always the case. And don't put it past an interviewer to give you an explanation that the explanation solution isn't even the one that you would use when you solve the problem. Because sometimes you do that, right? Like sometimes the problem statement will say like any of the solutions returned will work, right? And the ones in the examples aren't actually the ones that you end up using. But in a problem like this, it can be very difficult. It feels greedy. You know, just the idea of like trying to, okay, I'm trying to make partitions. I'm trying to fill partitions up to K. It feels greedy in itself. And then you see the solution explanation, right, is the greedy approach. So probably is a greedy problem. So just try that, you know, and if you don't get it and it ends up being wrong, well, then it's luck of the draw. Sometimes these problems, and my rant will be done, and I'll do the problem in a second, but sometimes these problems, they just come down to luck, right? You're as prepared as you can possibly be. You're either given a problem that you can solve and because you know it, or you've seen something similar, or you have strong intuition about that problem for whatever reason, or you haven't seen the problem and you have an idea, and maybe that idea is 50% likely to be correct and maybe it's not. So you have a 50%, you know, if it's 50-50, 50% you know it, 50% you don't. 50% of the time you get the problem, 50% of the time, only 50% of that you get it. So 75% time you get the problem, right? So there's 75% push through, that's more than enough. If that didn't make any sense, who cares? It has nothing to do with the problem, just more about Leetcoding and software engineering, interviewing procedures in general. But with that said, let's go ahead and get right into this problem. So what we did, right, is we just kept count of the current size of what we were looking at, right? And when it exceeded K, we knew that we had to backtrack, right? So we'll do a current count size, and then we'll keep track of how many partitions we've done, okay? Now, you always start with one partition, right? Because the whole thing in itself is a partition. Every time you add a split, it increases the size of the partition, right? When I add this split, it becomes 2 partitions, right? There's the uncolored region and the colored region. When I add this split, there's 3 partitions, right? There's this colored region, and the uncolored region. When I add this split, there's 3 partitions, and then when I add this split, there's 4 partitions, right? So just note that there's always 1 partition when you start. Okay, so we have our 1 partition. And then the count in total would be 1. And we look at our count in comparison to K and say, well, count is less than K, so we might as well continue and increase the size of C, right? So if we increase the size of C, we would add in the additional digits, so that would make C 16. And our partition size is still 1 because we haven't decided to do any partition. And we'd say, okay, 16 is still less than 60, so let's increase our size of our current count C again and see what we get. We notice here that we push our luck, right? Because now 165 is greater than 60. So we can't fit 165 in one partition. So that means we need to take the previous thing, turn it into a partition, and restart our count. So this is no longer 165. We zero it out and add in whatever C is. And so we notice when we added it in, it got too big, so we had to increase our partition and restart our count. So when we increase our partition, that's identical to saying, okay, this is now one partition. Now we have 5. We say, okay, is 5 less than 60? No. Now we look at 54, and we have 54. Still partition size 2, because we look at 54, we say, yeah, it's less than 60. Then we have 546, and we say, okay, this is too big. We'll restart this at 6, increase our partition size to 3. Make this another partition. We look at 6, look at 60, say it's not. We look at 62. We say, oh shoot, 62 is greater than 60, so the previous thing has to be its own partition. We'll restart at 2, and we will increase the size of the total number of partitions. And that's it. And then when you're done, you'll know that you'll actually never look at the last element, right? But since we said that the colored region and the uncolored, right, because well, sorry, this is all previous problems that I've done. Isn't that fun? You can see everything I've done before. Doesn't matter. If you're not ever going to actually, because you always change, like I drew these partitions after I went over the limit, right? So after I exceeded K, I created a partition for the previous values, right? Like at this value, I created a partition and I colored this region, right? At this value, I created a partition to color this region. At this value, I created a partition to color this region. But since there's no number here, my code won't look at this region to color this partition. So since I stated that the uncolored portion is a partition, in total there's 1, 2, 3, 4 partitions in total, right? Because I account for the fact there's one uncolored partition here in the beginning. Right, you'll always end up with one uncolored partition because there's never an additional number to check this previous thing. So that's more of a statement about how I write this code. Of course, you could probably write the code by adding a dummy variable or something. I don't know. But this seems a little more simple, I guess. This is a simple approach. So let's go ahead and do that. So we'll create our value C, which will be our current count. So how many values the value we've accumulated in our current partition. And then the total number of partitions. C will start at 0, and our partition will start at 1. We're going to look at each number x, I guess we'll call it x, and map int s. So we're going to turn s into each s character into an integer, because we need to treat these as integers to know what the value of the system is. And then in order to accumulate c, right, we multiply c by 10, and we add the digit s. Right? To get from 5 to 54, what do? You take 5, you multiply it by 10 to shift it over 1 to the left. Right? If you had the string 5, 4, right? In this system, we have 5 first. And then how do we make it 54? Well, we know that we moved 1 to the left, so we have to multiply 5 times 10 and then add 4 to get 54. So this should be a similar, a familiar approach, right? Dealing with numbers and trying to accumulate numbers and take a string, convert it to a number, whatever. Okay, so first thing we ask is we say, well, if we're gonna take C, if we take C and add in the current the current number that we're looking at, right? Like we made that decision here, right? If I take C, which is 16, and I add in 5, so it becomes 165, does it exceed 60? If that happens, you have to reset C to 0 and update your partition. Right, so if 10 times C plus X is greater than K, Well, then you have to add one to your partition, right? So now we just partitioned, but since we partitioned, we've taken all of the current things in our partition and moved it to the previous partition, and we're starting with a brand new partition with nothing inside it. And then at the end, you just take C and you say C equals 10 times C plus X. And then at the end, you just return the number of partitions that you have in total. Now, this code is almost correct. The only thing is it doesn't address this example here, right? Because in this example, what our code will do, unfortunately, is it will give us a response of size 6, right? Because with our code, if we looked at this example, right, unfortunately, there's kind of a bug, which is, you know, if k equals 5, for example, so let's say k equals 5, and then we had our count C and our count P. Well, k equals 5, 2, so we'd look at 2, we'd say our partition is 1, we'd add 3, right, we'd say 23, no, 23 is too big, so we increase our partition and add in 3. All right, we look at 8, we'd add in 8, we say 38 is greater than our partition, so we'll just add an 8 and make this 3. But this is greater than our partition too, and I can't make it smaller. So if the current value we look at, even after we zero out, is still greater than our partition, then we're in trouble. So basically, if any single character, right, because that's the only issue, right? So if we do this problem, if x itself is greater than k, we return -1. Right? That's basically the idea. If x itself is greater than k, then we're done. Right? Because there's no way we can split smaller than just the digit itself. So that should fix this issue. And with that, let's submit it. And let's pray. Ah! Be mature. Ah! Hey. Okay. So what's our time and our space? I have no idea. I haven't even thought about it. To be honest with you. I can't even. Right. All right. Space time. I'm a space time rocket ship. So if n equals the length of s and k equals k, well, we just have to look at each character in s. So we're going to have to look at all n characters in s. We convert it to an integer. That's a constant operation. We do a constant check here, a constant check here, constant update, constant update, constant update. So everything in here is constant. So for n things, we do something constant. So that's just big O of n. And then for space, well, we just create this these two variables here. So just constant. It doesn't relate to n or k. And when we use a map, we can use a generator object, right? So this is a generator object, so it's just going to process each string one at a time. It's not going to create a whole new array of size n. It'll just process them one at a time. So you'll also get constant. So everything's constant, so it's O of 1. And yeah, I should probably now slowly adjust the speed and tone of my voice so you know it's the end of the video. All right, guys, that's pretty much it for this one. Definitely, in summary, just consider the fact that you should split your string into, you should use the explanation and your intuition about how this seems like a greedy problem and the solution is greedy to just go ahead and try a greedy solution. And maybe think through, you know, hand-wavy proof as to why something is the way that it is. I personally don't have a really strong, you know, math theory background, so sometimes these problems can trip me up. But, you know, you got to work with what you got. Peace out.